Hello and welcome back to Educator.com and welcome back to Physical Chemistry. So today we're going to begin our discussion of thermodynamics, and we're going to begin with energy and the first law of thermodynamics. The next several lessons, what they're going to be is primarily just a theoretical discussion, background discussion, basic information. Some of this information you already will know from general chemistry. Some of it may be new to you, or some of it we'll be looking at it in a way that perhaps you haven't looked at before. So for the most part, this is just a collection of definitions and facts and things that we're going to be using, terms that we're going to be using, making sure that everything is defined well so that when we run into these things and use them on a regular basis, we'll know what it is that we're talking about. One thing I should let you know about the nature of physical chemistry in general, we're going to be doing a lot of example problems in this course, and by a lot, I mean a lot. And we will be doing them in the lessons themselves, although due to the nature of the course, what's going to be happening is many of the lessons are going to be presented, and there's going to be a lot of theoretical discussion or just general discussion of principles and processes. And again, although we will be doing some of the example problems within the lessons themselves, I'm going to save the bulk of the example problems to do in separate lessons altogether. It simply works out better that way given the nature of this particular course. So having said that, let's go ahead and jump right on in. Okay, so let's see what we have here. So what I'm going to do is start off by discussing the big picture of thermodynamics, something that isn't often talked about in most general chemistry course or in most thermodynamics courses, but we want you to have a big picture and then we want to close in. So, the big picture. Okay, there are three properties that, let me write this a little bit, make a little bit more room. And in fact, I think I'm going to go with blue, because I like blue. Okay. So, the big picture. Three properties completely describe the thermodynamic state of any system. Completely describe the thermodynamic state of any system. And this might be a bit of a surprise when you see this. State of any system. Any system. They are the temperature, T, the energy, we'll use the variable U for energy, and the entropy. Now, you've heard these terms before. Entropy, we're going to use S. If you know the temperature of the system, if you know how much energy the system contains, and if you know the entropy of the system, these three are all you need for a complete thermodynamic description. Now, you're probably wondering, well, wait a minute, what happened to enthalpy? What happened to free energy? Okay. Now, properties such as enthalpy, which you know of as H, or delta H, the change in enthalpy, and free energy, which you know of as G, the Gibbs free energy. These are actually derived properties. Derived properties. They're accounting devices used to either simplify calculations, make something more experimentally easy to deal with. So they are not actual thermodynamic properties. So I'll just call them, so they are accounting devices. And you'll see what we mean when we actually discuss them. Accounting devices. Okay. Now, each of the three fundamental thermodynamic properties it has an associated law. Has an associated law. And again, this might be a bit of a surprise what I'm about to write down. Now, you've heard of the first law of thermodynamics, the second law, the third law. You might not remember what it is that they are, but you know that there's a first, a second, and a third law. However, temperature, energy, and entropy are not the first, the second, and the third law. As it turns out, the temperature is associated with something that we call the zeroth law. And again, we're not going to concern ourselves with what it is right now. It just happens to do with temperature. Energy, that's the one that's associated with the first law. And entropy, that's associated with the second law. When thermodynamics developed, the reason we call it the zeroth law is it was sort of a logical realization. Once the first, second, and third laws were established, or once thermodynamics, classical thermodynamics was set in place, we stopped and we said, well, wait a minute. We need to somehow deal with this notion of temperature just to sort of bolster up this formal system, the logic behind what is an empirical study. I mean, that's the thing. Classical thermodynamics is entirely empirical. So we sort of went back and said, okay, let's tighten this up a little bit. We need to logically go back and, talk about this thing called temperature before we can actually move forward. So because they had already used the number 1, they decided to call it the zeroth law. So temperature, zeroth law, energy, first law, entropy, second law. Okay. Now, the third law is less general, and it only applies just to one class of substance, a crystal, and under a specific set of conditions, basically 0 degrees Kelvin. These are general laws, the zeroth, the first, and the second. The third law is less general. We will be discussing it, but as far as the properties themselves are concerned, this is the relationship. Now, we're going to begin our discussion with energy and the first law. So, let's see. We will begin with energy and the first law. Okay, so let's go ahead and get started. So when we speak about a thermodynamic scenario, we speak of a system and its surroundings. We speak of a system and its surroundings. Separated by a boundary. Separated by a boundary. So, schematically, we have something like this. We have, let's say, we can do it over here. It's not a problem. So this is going to be our system. This is going to be our surroundings. And this is going to be our boundary. That's it. It's up to us what we want to describe as our system, what we want to choose as our surroundings, what we want to choose as our boundary. Now the system plus the surroundings equals what we call the universe. That's it. Now, in some cases, the distinction between system and surroundings is very, very clear. So, for example, if I had a beaker of water, let's say at 100 degrees Celsius, so this is our system. And the surroundings would be the air outside. The boundary would be the actual beaker itself, the glass. Technically, the boundary is the inside surface of the glass. So technically, it's where the system just separates from the surroundings. So the glass itself is actually considered part of the surroundings. Where they meet, the inside surface where the water touches the glass, that's actually the boundary. You know that in certain circumstances, let's say if you have some beaker and you're running some endothermic reaction on that, an endothermic reaction is a reaction that absorbs heat. Well, what happens is the beaker gets cold to your touch. Well, what's happening here is that the heat that is required, that's being absorbed by the particular reaction, is being absorbed initially not from the surrounding air, it's being absorbed from the glass itself. Heat is being pulled from the glass, which is why when you touch it, it feels cold. Well, eventually, heat from the surrounding air will move into the glass. That will happen. So, by some process, yes, heat is coming in from the surroundings, but the initial heat is actually coming from the glass itself, which is why the glass feels cold. So again, the inside surface of the particular beaker is the technical boundary, but for all practical purposes, it doesn't matter. Okay, in other cases, it's not so clear what the boundary is. And this is often the case in chemistry. So in other cases, don't need a comma there, the boundary is less clear. Boundary is less clear. And a perfect example of that is, let's say, the reaction of potassium hydroxide plus hydrochloric acid giving us water. I tend to write water as HOH just to remind myself that it is an H and an OH in a neutralization reaction, plus potassium chloride. Well, in this particular case, so the surroundings is the water. The system is the reaction itself. There is no clear, distinct boundary that we can see when it comes to a reaction. We're running a reaction in an aqueous medium. The reaction is either going to be endothermic or exothermic. It's going to absorb heat or release heat. When we draw schematically, we can just, again, draw a little box or a circle or whatever you want. It's the reaction that's the system. And in this particular case, the aqueous environment around it, that's the surroundings. So there is no clear, distinct boundary, but we can always choose an appropriate boundary, or an idealized boundary in this case, in order to discuss it. So the reaction is the system. And the aqueous environment is the surroundings. And again, the boundary not so clear, but it is there in some sense. Okay, so let's go ahead and... Now, we speak about the state of a system. You're going to hear the word state a lot in thermodynamics. So we speak about the state of a system. And the state is when each of the system's properties has a given value. Has a given value. Now, the particular system itself will decide what those properties are. In the case of, let's say, a gas, pretty much all we need is the pressure, the volume, the temperature, and let's go ahead and use the PV equals nRT and the number of moles. So if we know the pressure, the volume, the temperature, and the number of moles, we know the gas is in that particular state. If we change any of those variables, we have a change of state. There's a new pressure, a new temperature, a new volume, and possibly a new number of moles. So that's it. Now, so we speak of a change in state, or a change of state. That is when the initial and final states are specified. Are specified. And again, there's nothing here that you don't already know, but we do want to formalize it to a fair extent. Being precise is going to be very, very important in thermodynamics. A lot of the definitions have very, very restricted meanings. Okay, specified. Now, we speak of speak of the path. It's going to be very, very important, the path for a change in state. The path is exactly what you think it is. It is the individual steps taken by a system in going from state initial to state final. So if we wanted to take a look, so let's see, let's do a quick for example, and we'll go ahead and use something that we're going to be using a lot of, a pressure volume graph. So pressure and volume, let's use one of the isotherms. You remember the isotherms? If you're going to keep a temperature constant, you're going to end up getting a graph, the relationship between pressure and volume. As pressure decreases, volume increases, or as volume increases, pressure decreases. This, if you perform the change in volume, change in pressure, and keep the temperature constant, it's going to follow something called an isotherm. Okay, so let's call this our initial state. Let's call this our final state. So let me go ahead and do SI and SF, initial and final state. The path in going from initial state to final state, I can do this many ways. I can go that way and then this way. I can go this way and that way. I can actually follow the isotherm. I can go this way. Let me go ahead and put little arrows like this. I can maybe go, all kinds of ways. I mean, if I want, I can go this way and back up and that way and that way, that way, that way, and then finally end up here. So there are different paths that I can actually take in going from initial state to final state. And the path is going to be very, very important later when we discuss work and heat. As it turns out, work and heat are path functions. How much work or how much work a system does or is done to, or how much heat is transferred to a system or from a system actually depends on the path that we take in going from an initial state to a final state. As it will turn out, and we'll see, energy itself, it doesn't matter what path we take. All that matters is the initial state and the final state. So in the case of work and heat, path is very, very important. And again, you know this already from your experience. If I want to fly from here to, let's say, New York, I can do it a couple of ways. I can just fly straight, or I can fly to Seattle first, then maybe to Miami, then go to New York. Well, the initial and final states are the same, but clearly I'm going to end up spending a lot more time, a lot more gas going to Seattle first, then to Miami, then to New York. So the path actually makes a difference. That's it. Okay, so let's go ahead and let's see. I think I'm going to go ahead and go to red just for a change of pace here. Now, let's define an open system. An open system is where both mass and energy can transfer to and from the system. In other words, it can cross the boundary. So, both mass and energy can cross the boundary. And by boundary, we're talking about the boundary between system and surroundings. Okay, a closed system. A closed system is one where only energy can cross the boundary, no mass. Cross the boundary. And of course, we have our final, which we call an isolated system. That's exactly what you think it is. It's where neither mass nor energy can cross the boundary. Neither mass nor energy can cross the boundary. Okay, now very, very, very important. An isolated system does not produce any observable effect in the surroundings. So, again, this is obvious, but we do want to state it. An isolated system does not produce any observable effect in its surroundings. Profoundly important. Okay, let me go ahead and go back to blue. I think I like blue a lot better. So, important questions. Important questions to ask for every scenario. So every scenario that you come across, every problem that you do, these are the questions that you want to keep in mind. And this is not the maximum list. I mean, you're obviously going to ask many, many questions, but these are the basic fundamental questions that you always want to be aware of. Scenario. Either explicitly or implicitly. Okay. What is the system? What is the surroundings? What is the boundary? You have to be very, very clear on these things. What is the boundary? What is the initial state? What's the final state? What is the path? Profoundly important. And I'll just put etc. for etc. Several other questions depending on the particular scenario. So you definitely want to keep these things in mind. Anytime you face a new problem, make sure that you know what your system is, what your surroundings are, what your boundary is, what your initial state is, what your final state is, what path you're taking. If you have these things, then you can go ahead and work out the rest, hopefully. That's going to be the test. Okay, let's talk about work and heat. So, you know what? I think I'm going to, yeah, it's fine. I'll go ahead and stick with, so let's go ahead and talk about work and heat. Profoundly important. So let's go ahead and begin with work. Let's give a nice definition here. Let's see, actually, you know what? I think I'm going to start on the next page. So let's start with work. These are very, very specific definitions. They're going to seem self-evident to some extent. Some of the things that I say may be flagrantly obvious, but we want to be very clear about them, which is why we're laying them out like this in such a formal manner. So, work is the process by which a quantity of energy flows. We'll also use the term transferred. Is transferred. Flows or is transferred across the boundary. The boundary between a system and surroundings, and which can be converted to the lifting of a weight in the surroundings. This is the most important part in the surroundings. So when we would talk about work that has flowed, work is energy. It's a quantity of energy that flows between system and surroundings. And this, as it turns out, this particular energy that flows is energy that can be used to lift a weight in the surroundings. Or if the work happens to flow from the surroundings to the system, leave the surroundings, the weight itself will go down. So when we talk about lifting a weight, we're talking either positive or negative. Okay, some notes on work. So, notes on work. Things to definitely keep in mind. Okay. 1. Work appears only during a change of state. Change of state. In other words, if there's a change of state, some kind of energy has flowed. If work shows up, that means the final state is not the same as the initial state of system or surroundings. So work appears only during a change of state. Work is recognized, identified as work by an effect in the surroundings. This is probably the most important part. In the surroundings. It's the surroundings, what happens, what we observe in the surroundings that lets us know what's actually happening in the system. It's indirect. We don't actually observe a system. We observe the effects of the surroundings, and that tells us what's happening in the system. Now, third part. The magnitude, in other words, the quantity itself, the magnitude of the work is mgh, mass times the acceleration of gravity times the height through which the particular weight in the surroundings has gone up or down. Now, work is a quantity, and because it's a quantity, and therefore, these 3 dots mean therefore, it can be positive or it can be negative. So, work can flow from the surroundings to the system. Work can flow from the system to the surroundings. In thermodynamics, we take a point of view. In thermodynamics, when we talk about energy that's flowing in the form of work or heat, we're talking about a direction. Positive and negative signs in thermodynamics, they have to do with direction. In and of themselves, they're not that important as long as we can keep track of the direction. So we can speak qualitatively. It's going from the system to the surroundings, from the surroundings to the system. We can keep that straight. Then we just have to deal with magnitudes. Positive and negative signs don't matter. But when we do the mathematics, we have to, any negative sign means that it's moving in a particular direction depending on what point of view we've taken first. So we have to decide, am I taking the surroundings point of view or am I taking the system's point of view? As it turns out, it doesn't really matter what point of view you take as long as you have a convention and you stick with that convention. And if the convention is different than anything that you've learned before or is a new convention that you've come across, all you're really doing is switching the signs. That's all you're doing is taking a positive, just putting a negative sign in front of it. So don't worry so much about conventions. We'll talk a little bit about that in a while. Okay, so let me see. So work is a quantity and therefore can be positive or negative. Okay, it is positive if a mass has been lifted in the surroundings. In other words, if h is positive, if the height through which the mass moves, if h is positive. In this particular case, we say work has flowed or flown to the surroundings. Or work has been produced in the surroundings. Work has been produced in the surroundings. That's it. So when we talk about work, it's going to be positive, from the surroundings point of view. If a weight has been lifted in the surroundings, work is positive. That means work has flown into the surroundings, normally from the system. Or work has been produced in the surroundings. So we'll use both of those descriptions. Now, work is over here, a little higher up here. Work is negative if a mass is lowered in the surroundings. In other words, if the height is negative, if a weight has dropped in the surroundings. Okay, now in this particular case, we say work has flowed from the surroundings. Or work has been destroyed. We'll use both descriptions. Work has been destroyed in the surroundings. Clearly, prepositions, very, very important in thermodynamics. From, to, in. Okay. And don't worry, we'll actually be discussing this in a lot more detail. So, let's see. So now let's talk about heat. Okay. Heat is, again, the process. Notice I'm using the word process in the definition of work and in the definition of heat. So it's the process by which a quantity of energy flows across the boundary between system and surroundings due to a difference in temperature between the system and surroundings. Now the heat itself flows from regions of higher temp to regions of lower temp. And we know this already. If you have something that is 100 degrees and if you have something that is 50 degrees and you put them into contact with each other, heat is going to flow from the 100 degrees to the 50 degrees. So the temperature of the 100 degrees is going to drop, the 50 degrees the temperature is going to rise, and it's going to come to some sort of a thermal equilibrium. There's going to be a final temperature that both of them will reach. That's it. Heat is not a thing. It is a quantity, but it's a process. It's what happens when you put two things in contact that are of different temperatures. All of a sudden, there is some spontaneous flow of energy. So that's what heat is, the process by which a quantity of energy flows across the boundary between the system and surroundings due to a difference in temperature between the two. Heat flows from regions of higher temp to regions of lower temp. That's it. Okay, now let's go ahead and say a few words about heat itself. So, notes on heat. Notes on heat. Okay, not altogether different than work. Heat appears only during a change of state. During a change of state. Okay. Heat is recognized by an effect, again, in the surroundings. By an effect in the surroundings. That's how we recognize heat. That heat has flowed. By what happens, we observe the surroundings. We don't observe the system. Okay. Now, this next one, I'll write it down. Not something that you really have to remember. Sort of keep in mind. Again, it's more of a formality. The magnitude of the heat is proportional to the mass of water in the surroundings that increases or decreases in temperature by 1 degree Celsius. Or let's just say 1 degree. I mean, you know, when we're working in thermodynamics, we're going to work in Kelvin. But you know what? I'm just going to write 1 degree. Okay, 1 degree. Make it more generic. So again, we said that the magnitude of the work was mass times acceleration times the height through which the particular weight in the surroundings moved. Analogously, the magnitude of the heat is going to be proportional to the mass of water in the surroundings that increases or decreases in temperature by 1 degree. So if there's a certain mass of water in the surroundings that ends up getting 2 degrees hotter, well, those 2 units of heat are going to be proportional to the amount of water that's actually there. It's going to be different if it's 10 grams or if it's going to be 100 grams. So again, this is more just a formal definition to keep it in line with the fact that we need some sort of physical apparatus, in this case water, by which to decide that heat has flowed. And this is how we decide if in the surroundings water has gotten hotter or colder. Okay. Let's see. Now, let's continue on. Okay. Heat is a quantity like work, and therefore it can be positive or negative. Now, in the case of heat, it is positive if a mass of water has cooled. And again, this mass of water is in the surroundings. So if the water cools down, that means heat has flowed away from it. Say heat has flowed from the surroundings. From the surroundings. If it's flowing from the surroundings, it's flowing to the system. That's it. It's surrounding system. It's not going to go anywhere else. Heat is negative if a mass of water has warmed. Heat has flowed to the surroundings. In the case of heat, it's flowed to the surroundings, it's flowed from the system. In chemistry, you're accustomed to always taking the system's point of view. Heat, the way we've defined it here, is the point of view that you're accustomed to. When we talk about heat being positive, that means heat has flown into the system. If heat is negative, that means the system has lost energy as heat. Heat has flowed away from the system. This is the convention that you're most accustomed to in chemistry, taking it from the system's point of view. Well, if it's positive and it's flowing, that means heat is flowing to the system. It's flowing from the surroundings. That's it. So it's just a question of perspective. Because we always recognize these things by what we observe in the surroundings, this is why we're using the surroundings as our point of view, as opposed to the system's point of view. But it really doesn't matter, because again, you have to decide where you're standing in order to decide whether something is coming or going. That's the whole idea. And again, we'll talk a little bit more about convention in just a minute. Okay, so let's see what else we've got. Okay, so this is going to be very, very important. So deciding, actually I'm not going to write this down, I'm just going to go ahead and say it. Deciding whether or not heat or work has flowed during a change of state is based strictly on observations of effects in the surroundings. This is profoundly, profoundly important. Let's clarify this. I'm going to run a couple of experiments. Okay, so when we have to decide whether heat has flowed or work has flowed, we don't look at the system. We look at the surroundings. I'm sorry to keep belaboring that point, but this is what we do in thermodynamics. We need to be very, very clear about what's going on. Yes, we're going to be talking about systems, and especially since this is physical chemistry and it's chemistry, we're going to be talking about chemical systems. We will be concerned with the system, but we don't just want to ignore the surroundings. It's very, very important to know that the information we get about the system comes from information that we observe in the surroundings. So I want to clarify this point. So let's run a couple of experiments here. So experiment number 1. Okay, I am going to set up I'm going to go ahead and take a beaker of water, okay? And I'm going to have 25 grams of water in here, and it's going to be at 25 degrees Celsius. Now I'm going to go ahead and immerse that in a larger beaker of water. In this particular case, this is going to be 100 grams of water, and it's going to be at, that's fine. Let's go ahead and put it at 80 degrees Celsius. 80 degrees Celsius. Okay, so this is our surroundings. This right here, the small beaker, the 25 grams of water, that's going to be our system. And the boundary is that right there. It's going to be the glass, the small beaker. So that's our boundary. Well, okay, so we already know what's going to happen. Due to the temperature difference, the 80 degrees and the 25 degrees, heat is going to flow from a hotter region to a colder region. So heat is going to flow from the surroundings into the system. So let's see what goes on. Now, here's what we do. We let the surroundings, we wait, a little bit of heat flows, we let the surroundings drop from 80 degrees Celsius to 79 degrees Celsius. So we let it drop by 1 degree, and then we take out this beaker. And then we take out the small beaker. Okay. Now, let's go ahead and do some calculations here. We know that the amount of heat that flows is equal to the mass times the heat capacity times the change in temperature. So, let's go ahead and call this Q out. This is going to be the heat that flowed from the 100 grams of water. That's going to equal mc delta T. Well, that's going to equal, there is 100 grams of water, right? the heat capacity of water. I'm going to go ahead and use just the calorie instead of the joule for right now. So it's going to be 1 calorie per gram per degree Celsius. That's the amount of heat energy that's required to raise 1 gram of water by 1 degree Celsius. Okay, and we let it drop by 1 degree Celsius. So we have 1 degree Celsius. When we go ahead and we do this math, 100 calories of heat have flowed from the surroundings to the system, which is the small beaker. Now, let's go ahead and calculate the amount of heat that has flown into the beaker and find out what its temperature is. So again, Q in, the system, is equal to mc delta T. In this particular case, we know what Q is. Q is 100 calories of heat. 100 calories have flowed. They flowed into 25 grams of water. 25 grams of water. Well, the specific heat of it's still water, so it is just 1 calorie per gram per degree Celsius. We want delta T. Well, when we solve for delta T, we're going to find out that delta T is 4 degrees Celsius. So now the small beaker of water is at 29 degrees Celsius. 1 degree Celsius drop in the surroundings. Now the beaker is at 29 degrees Celsius. Okay, that's our first experiment. We took a small beaker, we raised it from 25 degrees to 25 degrees to 29 degrees by a flow of heat. Okay, now let's do our second experiment. So let's go here, jump forward a little bit. Okay, this is called a Jewel Apparatus. Basically, if I take that beaker, that small beaker, I can set up this kind of apparatus. This is going to be our beaker right here, our beaker of water. Now what I can do is I can set up this system right here. Basically what it is I can put a paddle wheel inside that beaker, and I can wrap a string around that paddle wheel, and I can attach that string to a weight. Notice there's a little ruler here. Now, I can go ahead and adjust the height through which well, you know what's going to happen. The weight is going to fall down. When it falls, it's going to turn this handle. That handle is going to turn the paddle wheel. The paddle wheel is going to stir up the water, and it's going to raise its temperature. Now, I can go ahead and pick a particular weight, and I can pick a particular height, and arrange to stir up the water enough to raise the temperature from 25 degrees to 29 degrees. That just comes from a choice. I can do a little bit of trial and error, and I can raise it. So we can arrange a mass and a height through which this mass drops such that we get a 4-degree rise in temperature. For our 25 grams of water. So notice, experiment 1, I have 25 grams of water that is now in a final state of 29 degrees Celsius. Experiment 2, I have 25 grams of water that is now at 29 degrees Celsius. Okay. In experiment 1, it reached 29 degrees Celsius by a flow of heat. In experiment 2, clearly there's no heat that's flowing here. What we're doing is work. We're actually doing work on the water, and by doing work on the system, we're actually raised its temperature to 29 degrees Celsius. Now, if you didn't see these experiments, if let's say you were out of the room and then let's say you came into the room and all of a sudden I presented to you two beakers, both of them 25 grams of water at 29 degrees Celsius, what can you do to decide which beaker had the heat flow, which beaker had the work flow? Well, without knowing the experiment, there's no way to decide. So just looking at the system, there's no way to decide whether a flow of heat has raised the temperature or whether a flow of work has been done, or whether a flow of work has actually raised the temperature. However, if you observe the surroundings, there is a way to tell. Now, let's recall. So, by observing the system, you cannot tell. All you see is this beaker at 29 degrees Celsius and the other beaker at 29 degrees Celsius. The question is undecidable. However, if you look at the surroundings, by observing the surroundings, you'll notice two things. In experiment 1, the surrounding is 1 degree cooler. Because it's 1 degree cooler, that means heat has flown from the surroundings. Therefore, you know that that particular beaker rose in temperature because of a flow of heat, a transfer of heat. In experiment 2, a mass in the surroundings is lower. You can see it with your own eyes. You look and you see that the mass is actually lower than it was before. Because you're observing it in the surroundings, if a mass is lower in the surroundings, that means work has been done. And since the mass is lower, that means work has been done on the system. Work has flown from the surroundings to the system. That's how you can tell. So, I mean, the point we're trying to make is that you can't tell just by looking at a system what has happened, whether heat has flowed or whether work has flowed. However, if you observe the surroundings, you can tell. 1 degree cooler in the surroundings, it's heat that has flown. A mass that's lower in the surroundings, it's work that has flown. So, again, it is effects observed in the surroundings that tell us what has happened in the system. In chemistry, again, we always take the system's point of view. There's not a problem with that, but we get so wrapped up in the system, we forget about the surroundings. Oftentimes we have to look to this, most of the time we have to look to the surroundings to let us know what's happening in the system. It's indirect. As it turns out, you already know this. This is not something that's really new to you. When you're doing thermodynamic experiments, you remember the calorimetry experiments that you did in general chemistry. In order to find out what the enthalpy of a particular reaction is, what the heat released or the heat absorbed is, you're not looking at the reaction itself. What you're doing is you're running the reaction in aqueous medium or in a bomb calorimeter, and what you're measuring is the temperature of the water change. That's what you're doing. You're taking a look at what's happening in the system by taking a look at what's happening in the surroundings, in the water. You're taking a look at whether the temperature of the water rises or goes down, and the extent to which it rises or goes down tells you how much energy is absorbed or released in the system. If the temperature of the solution of the aqueous environment goes up, that means that heat has flown into the surroundings to make it hotter. Well, if heat has flown into the surroundings, that means that heat has flown out of the system. And since our reaction is the system, that means it's an exothermic reaction. So you know this already. We don't observe the system. We observe the surroundings to tell us what's happening in the system. Okay. Now, let's go ahead and say a couple of more. So, a little bit more on work and heat. Now, work and heat, they are energy. Okay. And they are quantities, as we said. Algebraic quantities. They're positive or negative, depending on the direction of flow. Quantities. But they are not properties that are possessed by a system. They are not properties possessed by a system. They are processes. By which energy is transferred. Okay. We never speak of a system having X joules of heat or Y joules of work. We never speak of a system having X joules of heat or, Y joules of work. What we do say we speak of a system having a given energy. Having a given energy. And in a change of state, if a change of state takes place, we say X joules is gained or lost as heat, or Y joules is gained or lost as work. Now, when we actually start talking about this, just, generally doing the problems and things like that, we're going to be a little more loose with the language. We're going to say X joules of heat has flowed. Y joules of work has flowed. They are things, but they are processes by which energy is transferred. That's what's important. So a system does not possess heat or work. Work and heat are things that happen upon a change of state. It's energy that changes. There's a beginning given amount of energy in a system, work or heat has flowed, and then there's a final energy of the system. The system possesses energy. Heat and work are the processes by which energy is actually transferred, by which the energy of the system changes. That's it. Okay. Y joules is gained or lost as work. Okay. And of course, now the system possesses, I use the word possesses, I'll just say has a new amount of energy, either more or less. New amount of energy, which is its final state. Okay. So energy moves via heat and work. I'm sorry to keep belaboring the point. I know you're probably getting sick of this, but it is really, really important to differentiate. I guess the best analogy that I can think of is the money analogy. You can go to a bank and you can deposit money or you can withdraw money. So money can be transferred. Well, you can deposit money as paper money or you can deposit it as coin money. It's the dollars that matter. You're going to start off with, let's say, $100 in your bank account. Let's say you bring in $50 of paper and you bring $25 in coin. Well, now the final dollar amount in your account is the 100 plus the 75 that you brought in. So now you have $175. Well, the money is energy. That's how much money you have. That's the dollars. The paper is the heat and the coin is the work. So you can bring money in as paper or as coin. So it's not money itself. It's not the actual value. It's just the means by which you're actually transferring it, if that makes sense. So again, money is the energy, paper is the heat, and coin is the work. Hope that makes sense. Okay, so let's go ahead and talk finally about some conventions. So, our conventions. Do not worry about conventions. They're not a big deal. Definitely don't get nervous about this. Like I said before, the chemistry convention is we always take the system's point of view. Our conventions are going to be slightly different. However, when I do the problems, I'm going to show you, I'm going to do it with our convention, and then I'm going to show you just how easy it is to actually do it with what you would call the purely chemist's convention. Literally, all I'm going to be doing is changing the sign. If I come up with a value of work for, let's say, 50 joules, from the chemist's point of view, it's just going to be negative 50 joules. The math itself doesn't change. All that changes is positive and negative signs. That's all. So again, I'm going to list it. It's going to seem like it's a big deal. It's absolutely not a big deal. I promise you, nothing is lost. The math is exactly the same. All the derivatives are the same. The integrals are the same. The only difference is a positive and negative sign. As long as you understand what the system is, what the boundary is, and the direction of heat flow and work flow, as long as you understand those things, that's what matters. When you give your answers on a quiz or a test, if you forget a negative sign, that's not a problem. You can always say heat is flowing from the system to the surroundings. As long as you specify the direction of flow, you actually don't even need to worry about a point of view. You don't need to worry about the positive and negative signs. The math itself is not that relevant. What's relevant is the magnitude of the change and the direction of the change. If you can keep track of that, everything will be fine. So having said that, let's talk about our conventions. Now, our convention for heat. We will say that heat is positive if it flows into the system. Okay? Which means from the surroundings. So again, it just depends on what your perspective is. We will call heat negative if it flows from the system. In other words, it flows to the surroundings. By not picking a particular point of view, by not getting locked into, quote, the chemist's point of view, or the engineer's point of view, or the physicist's point of view, what you're doing is you're freeing yourself up to actually just take a look at a thermodynamic scenario in general. If you understand that, point of view becomes completely secondary and irrelevant. Afterward, once you decide what's going on, where energy has flowed, where it's ended up, what the final temperature is of the system, what the initial temperature is, and the final temperature is of the surroundings. Once you have the bird's eye view, the big picture, you can decide yourself what point of view to take if you have to give a final answer. It's the scenario, the process that we want to understand. We don't just want to get locked into a particular point of view. Oh no, I have to take the system's point of view. You don't. That's it. I just want to sort of pull you back to give you the bigger picture. That's what's important. Okay, so negative, it flows from the system or to the surroundings. Now, our conventions for work. Okay, work is positive if it flows to the surroundings, which means from the system. And work is negative when it flows from the surroundings or flows to the system. Let's go ahead and give a schematic representation of what it is we're talking about here. So we have our surroundings. So we have our system here. We have our surroundings here. Okay. Heat positive. Heat negative. Heat is positive when it goes into the system from the surroundings. Heat is negative when it goes out of the system to the surroundings. Work is positive when it comes to the surroundings from the system. Work is negative when it goes from the surroundings to the system. This is a schematic of our particular convention. And again, don't worry about the convention. All of this will make sense when we actually start doing the problems, and you'll see that it absolutely does not matter what convention you take. Physicists take one point of view, engineers take another point of view, chemists take another point of view. If you understand the thermodynamics, the conventions become irrelevant. They become secondary. They become important only when you have to give a final answer for a final thing. If I ask you about a system, then once you know what's happening, you can tell me, yes, heat has flowed to the system, work has flown out of the system, and the final energy of the system is this amount. Thermodynamics we want to understand. The flow that we want to understand. We don't want to get locked into just one point of view and feel, oh my God, you know, if I don't take that point of view, everything is going to fall apart. It won't fall apart, I promise you. Thank you for joining us here at Educator.com. We'll see you next time. Bye-bye.